Hey programmers, Alvin here. Right now I want to go over the approach for this bottom right value problem. So in this problem we want to take in the root of a binary tree and return the rightmost node in the bottom level of that tree. So what does that mean? First we have to understand what a level refers to. So I can look at the very first level of this tree and I can designate it as level 0. So a level just goes across the tree, right? And then from there I can look at level 1, just the B and C going across, then also level 2 going across of D, E, and F. And there's no level greater than level 2, so we'll say level 2 is the bottommost level, but in particular I want to focus on the rightmost node of that bottom level. And that's why for this particular input we say that the bottom rightmost value is going to be F, and we just want to return that in our function. So let's take a look at another example. Say we're given this binary tree. Let's first find the bottom level in a similar way, right? So here I have level 0, then level 1, then level 2, and also level 3, and there's no other levels below this. And I would just return the value of the X node over here. Notice that X is definitely the rightmost node of this level, although it's actually not connected via a dot right pointer, right? If you kind of look at X's parent, technically X is the left child of U, but that doesn't matter because in the grand scheme of things, we still see that X is the rightmost node of the bottom level. So you should still return X in this instance. So how can we go about solving a problem like this? Well, since this is a tree problem, you should immediately think of either your depth first or breadth first algorithms. And I think in particular, breadth first is going to be a very useful one in this scenario. So let's take a look at how we can use a breadth first traversal to solve this. Let's say I was given this as our tree, and we're going to step through this specific example. Just by visually looking at this tree, you can see that in the end, we should return the E node. Cool. And what I'll do is I'll overall just go for a classic breadth first traversal, but I need to be sure that it also travels from left to right. And if I do this correctly, that means that the very, very last node that leaves my queue, or the last node I visit, should technically be the bottom rightmost node. So just to review, let's step through how this breadth first algorithm would flow. I start with a queue, and so I'm going to add things to the back of my queue, and they exit through the front of my queue. And I'll start by initializing my queue with the root node on it. So I'm going to put A on my queue. Then from there, I'm going to need to track the current thing that leaves the front of the queue, so I'll get that set up. And so we begin our first iteration of this algorithm. We remove A from the front of the queue, so that's our current. And I'll just kind of mark this as visited just visually. And then from there, I'll just keep running this algorithm, right? I know that I look at A's children, I look at its children B and C, I'm just going to add those children into the queue. However, I'm going to be sure to put my left child B and then my right child C. And what does that establish? Well, if I make sure I add my left child before my right child, then I know that in the grand scheme of things, my right child is going to be visited later, right? And that's an important aspect of this solution. So we'll continue this algorithm. We remove the front of our queue. So we have B as our current. I look at B's children, and I go ahead and I add them into my queue. So I add D followed by E. Again, put your left first and then your right. At this point, I have another iteration. My current is C. I can just mark it off. C has no children, so I don't need to add anything into the queue. Now I remove the front element of D from my queue. D also has no children, so nothing happens here. And then finally, when E leaves the queue, E also has no children, so it adds nothing into the queue. And at this point, it looks like my queue is empty, which we know is our classic stopping condition for our breadth first traversal. Right? So as soon as the queue is empty, I know that I must have visited every node of the binary tree. And if I look at the last value I stored in current, it is the E node. And in general, it's going to refer to the bottom rightmost node. And this should make some sense because if we think about a breadth first traversal, you're only going to go down to a new level once you've completed your current level, right? And if I also guarantee that this breadth first travels from left to right, then on the very, very last iteration of my traversal, I will have touched the final bottom rightmost node. Cool. So that seems like a very straightforward solution. What can we say about the complexity of this? Well, nothing too fancy here. We know that n is going to be the number of nodes. And in terms of the time complexity, this is just a regular breadth first. So every node is entering the queue once and also leaving the queue once. That's going to run in O of n time, right? And that's assuming that our queue operations of adding to the back of my queue and removing from the front are themselves O of 1 constant time. And we also need to store the cube, so our space complexity is just going to be O of n. Now that being said, this is actually a pretty easy algorithm to implement, although it's kind of tricky to come up with this idea in the first place. I recommend you try to implement this algorithm on your own, and if you get stuck, I'll catch you in the walkthrough video.